In this video, we will explore Newton's second law of motion by discussing the key points of the law and exploring the equation, the net force equals the mass times the acceleration. Newton's second law will then be applied in a variety of situations, carefully detailing how the net force and the acceleration of an object are related. Newton's second law states that the rate of change of motion of an object is directly proportional to the net force and inversely proportional to the object's mass. It is made in the direction of the straight line in which the force is impressed. The key ideas are that the acceleration of an object is directly proportional to the net force that's acting on it, and that the acceleration and the net force will be in the same direction. The resulting acceleration will be inversely proportional to the object's mass. From this statement, the formula for the acceleration of an object can be written as the net force divided by the mass. Recall that the net force is the vector sum of all the forces. This relationship shows that the acceleration is inversely proportional to the mass. Often Newton's second law is written in terms of the net force, and the net force equals the mass times the acceleration. Writing the equation in this form shows that the net force is directly proportional to the acceleration, with the mass being the constant of proportionality. Let's explore Newton's second law by applying it in a variety of situations. Let's start by finding the acceleration of a 2 kilogram block on a frictionless surface with a horizontal applied force of 10 newtons acting on it. A free body diagram for the block will show the force of gravity acting down and the normal force acting upward. If no other forces act on the block, it will have no acceleration and is said to be in translational equilibrium. But if a horizontal force is applied to the block will now have an unbalanced or net force acting on it. Considering the vertical and horizontal components, we can see that in the vertical dimension, the net force is equal to 0, so the magnitude of the normal force must be equal to the force of gravity, and there's no acceleration in this dimension. The net force acting on the block will equal the applied force in the horizontal dimension. According to Newton's second law, this net force will cause the block to accelerate in the same direction, with the magnitude of the acceleration equal to the applied force divided by the mass. Substituting the known values into this equation, the acceleration of the block can be found to be 5 meters per second squared. Let's take the same situation, but replace the frictionless surface with a rough surface, with a coefficient of dynamic friction between the surfaces of 0.2. Let's assume that this dynamic force of friction has a smaller magnitude than the applied force. The free body diagram will again show the force of gravity pointing down, and the normal force will point upwards, perpendicular to the surface. The applied force will point to the right, and now a friction force will point to the left, opposing the motion. Recall that the force of dynamic friction is equal to the coefficient of dynamic friction times the normal force, and the force of gravity is equal to the mass times the gravitational field strength. By considering the vertical forces, we can see that the normal force is equal in magnitude to the force of gravity. In the horizontal dimension, the applied force is acting to the right, and the friction force is opposing it, pointing to the left. These forces are not equal in magnitude, so there must be a net force acting in the horizontal dimension equal to the vector sum of these forces. Notice that because these forces are in opposite directions, a sign convention has been used, with the direction of the net force set as the positive direction. Substituting into the friction formula, and the formula for the force of gravity, the net force will be equal to the applied force minus the coefficient of dynamic friction times the mass times the gravitational field strength. This net force can be substituted into Newton's second law to find the new acceleration of the block when friction is considered. By substituting the known values into this equation, the acceleration of the block can be found to be 3 meters per second squared. If the direction of the applied force is rotated so that the force is now applied at a 20-degree angle to the horizontal, vector components must be considered, and the example becomes more complicated. The vertical component of the applied force is equal to the applied force times the sine of 20 degrees, and the horizontal component of the applied force is equal to the applied force times the cos of 20 degrees. The force of gravity again will be acting down on the mass, and a normal force will be acting upwards. The force of friction will oppose the motion and will act to the left. In the vertical dimension, the force of gravity is now balanced by two upward forces, the normal force and the vertical component of the applied force. Because there's no acceleration in the vertical dimension, the magnitude of the force of gravity will equal the sum of the normal force and the vertical component of the applied force. Rearranging for the normal force, we can see that the normal force acting between the block and the surface reduces in magnitude and is equal to the force of gravity minus the vertical component of the applied force. We will use this expression for the normal force later in the formula for the force of friction. In the horizontal dimension, the horizontal component of the applied force points to the right, and the friction force is pointing to the left. Because the horizontal forces are not balanced, there must be a net force in this dimension equal to the horizontal component of the applied force minus the force of friction. By substituting the formula for the force of friction, replacing the normal force with the expression for the normal force, and substituting for the force of gravity, an expression for the net force acting on the block can be found. Substituting the given values and solving, we can see that the magnitude of the net force is 6.2 newtons. Substituting this value into Newton's second law and solving, we can find that the acceleration of the block is 3.1 meters per second squared. Now let's consider the example of the block on an inclined plane, inclined at a 30-degree angle to the horizontal. And let's find the acceleration of the block as it slides down the plane, assuming there's a frictional force acting between the plane and the block. A free body diagram for the block will show the force of gravity acting down and the normal force acting perpendicular to the surface of the plane. The force of dynamic friction will point up the plane, opposing the motion of the block. When analyzing forces, it's always best to resolve the components in the direction of the acceleration and perpendicular to the direction of acceleration. For this reason, the vector components of force of gravity into the plane and along the plane must be considered. If we consider the forces acting into the plane, the block is accelerating down the inclined plane, so there's no net force acting perpendicular to the plane. The component of the force of gravity perpendicular to the plane is balanced by the normal force. So the normal force will be equal in magnitude to the force of gravity times the cosine of 30 degrees. Considering the forces acting parallel to the plane, the component of the force of gravity is acting down the incline, and the force of friction is acting up the incline. The net force must be acting down the inclined plane in the same direction as the acceleration. Using the direction of the acceleration as the positive direction, we can set up our equation for the net force by adding the forces acting in this dimension. The net force is equal to the component of the gravitational force acting down the incline minus the friction force. Substituting the formula for the force of friction into this expression, and then replacing the normal force with the known relationship, and finally substituting the force of gravity in, we can arrive at an expression for the net force acting on the mass. This net force can then be substituted into Newton's second law and solved for the acceleration. Note that the mass of the block will cancel out of this expression, so the acceleration is independent of the mass of the block. Substituting the known values and solving yields an acceleration of 3.2 meters per second squared. Another common application of Newton's second law involves a person in an elevator. Consider a 100-kilogram person standing on a scale in an elevator. Find the reading on the scale in each case. The key to this type of question is to recognize that the reading on the scale is representative of the normal force that the scale applies to the person. If the elevator is at rest or moving at a constant speed, a free body diagram for the person shows the force of gravity acting downwards and the normal force acting upwards from the scale. The force of gravity is a constant value, but the magnitude of the normal force will depend on the motion of the elevator. The net force acting on the person is the vector sum of the normal force and the force of gravity. So if the elevator is moving at a constant speed, or at rest, then these two forces are equal in magnitude and the net force is equal to 0 newtons. By applying Newton's second law, with an acceleration equal to 0, we can see that the normal force must be equal to the force of gravity. The scale will measure the normal force and then convert it into a measurement of mass by dividing by the gravitational constant. In this case, because the normal force is equal to the force of gravity, the scale will read an accurate measurement of 100 kilograms. If the elevator is accelerating upwards at 2 meters per second squared, then there must be an upward net force creating by the magnitude of the normal force increasing. The normal force will be larger in magnitude than the force of gravity, creating a net force pointing upwards, equal to the normal force minus the force of gravity. Applying Newton's second law with this net force, we can find an expression for the normal force needed to create this upwards acceleration. Subbing in the values of the mass and the acceleration, we can find the normal force acting on the person has increased to 1200 newtons. The normal force is increased and is not only supporting the person against gravity, but also providing additional force to accelerate the person upwards. The scale will convert this normal force by dividing it by the gravitational field strength and will read a new mass of 120 kilograms. Note that the mass of the person is still 100 kilograms. The scale gives a false reading of mass. In this case, the acceleration is upwards. This could mean that either the elevator is moving upwards and speeding up, or moving downwards and slowing down. If the elevator is accelerating downwards at 2 meters per second squared, then the net force must also be in the downward direction, created by the magnitude of the normal force decreasing. The net force will equal the force of gravity minus the normal force. Applying Newton's second law with this net force, we can find an expression for the normal force needed to create the downwards acceleration. Note that in assigning the directions of the vectors in this example, the direction of acceleration is set to positive. Substituting the given values for the mass and the acceleration, the normal force can be found to be 780 newtons. The magnitude of the normal force is now less than the gravitational force, and the person accelerates downwards as a result. The scale will then convert this normal force into a mass of 80 kilograms. Again, the mass of the person is still 100 kilograms, and the scale is giving a false reading. The acceleration is downwards, meaning that the elevator is either moving upwards and slowing down, or moving downwards and speeding up. Let's consider a more complicated elevator example. If there's a 2-kilogram block on a spring with a 20 Newton per meter spring constant attached to the ceiling of the elevator, and the elevator is accelerating downwards at 2 meters per second squared, find the change in length of the spring from its equilibrium position. A free body diagram for the block would show the force of gravity acting down, and the spring would provide an upwards force, which according to Hooke's law would be equal in magnitude to the spring constant times the change in length of spring. The gravitational force is equal to the mass times the gravitational field strength. The net force acting on the block is equal to the vector sum of these two forces, the force of gravity minus the spring force. By substituting the equations for the spring force and the force of gravity into the net force, we can find the equation for the net force. We can then go on to apply Newton's second law with this expression for the net force and rearrange it to find the change in length of the spring. Substituting the known values into this equation, we can find that the change in length of the spring will be 0.78 meters. This is a smaller extension than the spring would have if the elevator were at rest or moving at a constant speed. In summary, Newton's second law shows that the net force acting on an object is directly proportional to its acceleration, with the mass of the object being the constant of proportionality. Mathematically, this can be described as the net force is equal to the mass times the acceleration. When applying Newton's second law, it's important to use a free body diagram, which can be used to find the net force acting on the object. Then Newton's second law can be applied to find the acceleration of the object. A good rule of thumb is to set the direction of the acceleration as the positive direction in these equations. Thanks for watching.